Thanks, Joe. All right, so common logs is where we're going to start off. And with common logs, first off, you have to understand is what the base is. And for common logs, the base is 10. So common logs, you got a base of 10. And you have to know that because for common logs, the base is not shown. So you get to the ACT or SAT, and you're going to see something just like that. And it's an easy problem when you know what it is and you know how to handle it, because they're not going to show the base. Every once in a blue moon, you'll see that 10 down there, but normally it's not there. And if you just see log for logarithm and no base indicated, then the base is 10. Which that reminds me, judging from some of your quizzes, please understand that the base of what the subscript after the log is a subscript, which means it's written below and it's usually smaller. So some of you, when you were writing your logarithms, you may have written something like this. And you meant this to be the base. Well, does that look like the base to you? It doesn't look like the base to me. Again, it's supposed to be a subscript, so just be careful with the notation. All right, so anyhow, that's the exact same thing, right? A log. What does it mean? Now, we already learned how to convert from exponent form to log form, right? You cannot forget that. That's a key thing. And so if you convert this, then it's going to be something like 10 to the, I don't know, I'll use an x equals 7. So the actual value of that is going to be somewhere around, somewhere between probably 0.5 and 0.9. Because 10 to the first is 10. So we got to go less than 10, something like that. All right, so again, just make sure that you understand that that base is not shown. All right, so what's number 2? Number 2 is, again, a base 10 to the x is going to equal 5. What is number 3? Again, base 10 to the 32.2 equals, oops, I'm backwards there. Base 10 to the x or y or whatever equals 32.2. That one's going to be 1 point something. Because 10 squared is 100. All the numbers between 10 and 100 are 1 point something value of the logarithm. Calculator is really easy to use. And I would think most of you guys on your calculator have the log button on the face of your calculator. It's not a menu. Make sure that you locate your log button, and these are really easy. Really, really easy. So the log button gives you the logarithms are exponents. So the log button gives you the exponent when you input the result. So again, just for clarity's sake, because we think better in exponent form, number 1 is 10 to the x power equals 392, right? That's what the problem is. Do you have to do that to punch in your calculator? Not at all. I'm just trying to get you to understand what the answer should be, right? Because now we know we all know the answer is going to be 1 point something. Because, I'm sorry, 2 point something, right? Because 10 to the first is 10, and 10 squared is 100, and we're between 100, 10 cubed is 1,000. So you're going to be between 10 squared and 10 cubed. All you do is, in your calculator, and again, you have to learn your syntax. For some of you, you probably have to hit the LOG button first, then the 392. For others, it's 392 and then the LOG button. So figure out which way it is for you. My calculator, it's 392 and then the LOG button. And I got x equals 2.5933. We're pretty much going to treat these like the trig functions in that a little bit of difference makes a big deal. So we don't want to round that off to 2.6. Because here would be the reality if you rounded that off to 2.6, then that's really the log of 398, 2.6. Well, we want the log of 392, and it's 2.5933. So 4 decimal places, because the round off makes a difference because you're dealing with an exponent. Okay, so again, these are really, really simple. This is 10 to whatever power. You can put a variable there if you want. Is 7,345. But you're just punching in the button. Really easy. Gee, I can punch that button. 7345 and log button. .3866. 3.866. 3.8660. There we go. Beautiful. How many of you have to punch the log button first? Okay, does anybody do the number first and then the log button? All right, just the older type calculators, most of them do it the other way now. I actually like the older ones. I think they're easier to work. All right, piece of cake. Go ahead and finish off those last two. Do 4 and 5. Just punching buttons. You don't need to convert it. I was just trying to show you so the answer would make sense to you, which you can always do when you're taking a quiz or a test. Change the form and see, does my answer make sense? Dawson, question? So interpret that. Interpret what that means. Think about it, and then I'll ask you in a minute. Was that a negative number 3? Did I write that right? Okay. Remember, a negative exponent is going to be then that base down in the denominator, right? So this is 1 over 10 to that power, 3.468. Okay, can anybody interpret why this thing says error or domain error? Domain, what does it say? Domain error, is that what it says? Or just error? What's going on? Somebody raise your hand. Tell me what's going on. Nobody knows? Okay, look, you guys have to start thinking. So here's where I was trying to lead you. A moment ago I said, let me put this in an exponent form to show you what's going on. Let me put this in an exponent form to show you what's going on. Is that, you doing that? Okay. Hey, be careful. You know, if you're in a quiz or test, you could always put it in exponent form to see if your answer makes sense. So did you put this in exponent form? How many put this in exponent form? Okay. So what does that tell you? Think about that. What's the situation, right? This is 10 to what power equals negative 3.5. So why do we have an error? Aiden? Why? How so? What's the problem? Why is that a problem? Why is that a problem? Dawson? What's the problem? So why is that a problem? Alex? The result is negative 3.5. We're trying to find the exponent. And we can have negative exponents because this, logarithms are exponents. This one has a negative 0.3468 exponent. So negative exponents are no problem. Sammy? Say it again. That's what number 3 is, because number 3 is 10 to what power equals 0.45? And the answer is 10 to the negative 0.3468 power equals 0.45. But notice the difference in these two looks. In this one, the negative is with the exponent, and in this one, the negative is with the result. So that's the difference in those two. You got a negative with the exponent here, no problem. As Aiden said already, negative here is the issue. Why is it an issue is my question. I mean, that is the issue. That negative right here, why is it a problem? Why do we get domain error? Shane? That is correct, right? How can you get a base to end up being negative? And the answer is you can't. Right? You can't. Our base is positive, right? It's not shown, but we have a positive base. I don't care what power you raise it to. How are you going to get it to be negative? Right? Because what does an exponent do? It tells you how many times to multiply the base times itself. So you got a positive always multiplying times a positive. 2 times, 3 times, 8 times, a 0.5 times, a 0.7 times. You can even do the base times itself a negative amount of times, but that's just 1 over the base times itself, which is positive times positive. So it's always positive times positive. How in the world are you going to get to negative? You can't get to negative, and that's why you have a domain error. Right? It's impossible to have a positive base and end up with a negative result. There's just no way to get there. There's no way to get there. And that's why it's a domain error. If you were to look at the graph of that function, the graph would not go past the y-axis, right? There would be no x values possible when you go past, right? Again, thinking of it this way, right? Remember, your domain are all the x values. So we can't have the curve anywhere over there, and it's not going to be. When we graph the inverse, so you guys look back to, I think, the first page. First page, maybe not the first page. About 12.3. Oops. Hey, hold on there. What are you doing there? Right, this one right here. Here's a logarithm. And see how it's not going past. There's no x values that are negative. Because you can't get a negative result. And the x in this case is the result of the base to its exponent, giving you the result. It can't happen. There's just no way to get a positive times a positive to end up being a negative. All right, whether you understand all that or not isn't that big of a deal. Just when your calculator says, as long as you punched it in correctly, if your calculator says error, it's because it's an error. It doesn't work. All right, B here. The 10 to the x button gives you the results when you input the exponent. 10 to the x button gives you the result when you input the exponent. So, again, just for clarity's sake, what's number 1 saying? Number 1 is saying 10 to the 4th power equals what? Right? See how much clearer that is to understand when we put it in the other form? I mean, okay, 10 to something, 10 to the 4th power. All right, so how do you do that? Well, again, you have a 10 to the x button. So for some of you, you're going to punch in 10 to the x button, then the 4. For Anna and Amma, was it? I think we're going to punch in 4 and then 10 to the x button. Whoever has it the other way. Maybe it was you, Grayson. All right, so I do 4 and then 10 to the x button. And of course, we shouldn't even need to punch this one in. What's 10 to the 4th power? That's a 1 with 4 zeros. It's 10,000. So you're just punching buttons. And again, a quiz or a test, you have time, you can go ahead and change forms because you understand exponent form a whole lot better and see if your answer makes sense. All right, go ahead and do the other three. Just punching in buttons. Punch, brothers, punch with care. Punch in the presence of the passenger. All right, 6.23 sounds like Avogadro to me. Does it sound like Avogadro to you? 6.23. No, number 2. But the exponent is 6.23. Doesn't that remind you of Avogadro? 6.023 times 10 to the. Look at that, amazing. All right, and this one is, whoa, it's a big number. 1,698,000. 243.7. You might say, Mr. Scarfy, I thought we took these to 4 decimal places. Look, we're not doing the exponent anymore. We're doing the result, all right? It's a whole different ball game. This is the result. You're already over 1 million. You're over 1.5 million. What's a little pittance to the right of the decimal point going to matter? But when you're doing an exponent and all you have is something to the right of the decimal point, it matters. So that's the difference. All right, what does number 3 end up being? 3.5 negative. All right, now this one we better go ahead and do decimal places, right? 1, 2, 3 zeros, 0.0003. Because, you know, what is this thing? I want to do this one just for clarity's sake. That's what this is, right? 10 to the negative 3.5 equals x, which is really 1 over 10 to the 3.5 equals x. And 10 cubed is 1,000. And 10 to the 4th is 10,000. So it's 1 over somewhere between 1,000 and 10,000, which is 0.0003, right? And that's an extraneous equal sign there from your first edition notes. And what's the other one? 1.7783, because again, it's a small number. Right? It's a small number. We'll go to 4 decimals. If it's not, we'll just round off. Any questions on those? Oh, excuse me. Any questions on those? Anybody? Okay, a couple special cases. Though we're using LOG on these special cases hold no matter what the base is. So again, no base shown, therefore the base is 10 because of the LOG. So we know these are base 10. So what is the value of these? Well, if you change form, you'll clearly see what the value is, right? So this thing is 10 to the first equals what? Right, 10 to the first. I did it backwards, didn't I? Oh well, such is life. Should have been 10 to what equals 1. There we go, right? Result is always after the logarithm. They equal the exponent. And Dawson, what was the answer? Yeah, this is always going to be 0. Always, 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 because any base to the 0 power is the base divided by itself, and that's 1. So if this was base 3, result 1, it would be 3 to the 0 power 1. Base, 2.5 to the 0 power 1. No matter what the base is, if the result is 1, then the value of the exponent is always 0. The value of the logarithm is always 0. The second one is the one I was doing a minute ago, which now you have an exponent of 1. And therefore, in this case, the answer is always going to be the base, right? Which in this case is 10. Whenever you have a 1 as the exponent, of course the answer is the base. If the base were 7 with a 1 equaling 1, then of course the answer is 7, etc., etc., etc. No big deal. All right, so you get a worksheet over those tonight, which isn't a hard worksheet. It's a lot of calculator, so it's a lot of punching, not a whole lot of other stuff. So I want to go on to the next lesson. Okay, so that was common logs. Now we got to deal with natural logarithms. Natural logarithm. And can anybody tell me what the base is for a natural logarithm? Brian, what do you think? Don't know? Can you tell me what the question is? Oh, okay, good. Looked like you were zoned out there for a minute. All right, anybody know the base of a natural logarithm? Come on, you have some things in front of you. You can figure it out. You really could. It's not hard. Grayson? Not X, but at least that's an answer. Alex? Not 1. What's the base of Noah? No. No. You got nobody in here should ever become a detective. All right? The perp will always get off. All right? You have no detective skills, I hate to say. All right, Noah? No. Yes. It is E. We finally get an E. Look at the calculator on your piece of paper. Didn't we just do this one? A logarithm. And what was the base? And isn't the other button show you the base to what exponent? So what is right there? Okay, hard to see on there. Maybe, hopefully easier on your paper. I don't know. Right? Can you see the E to the X right there? Ah, yeah. All right. You guys make lousy detectors. Look, it's even boxed in yellow. I bet I say E somewhere else down the road on your notes there. Is it grainy? Yeah, you know, that's, what can I say? It's the way it goes. All right, well, just like common logs, the base 10 is not shown. For natural logs, the base is not shown as well. So how are you going to know whether it's a natural log or a common log? Well, it's real simplistic. I'm going to do this in blue, but it's an ln, not an log. And usually it's a script L and a script N. But again, when you're desktop publishing, it depends on what fonts you have available to you. You know, 20 years ago, there were less fonts available than there are today. Then you were pecking it out on a typewriter. Make a mistake, rip out your page, throw it in the garbage can. You know, you're writing your 10-page term paper, and you make a mistake, or you want to edit it, where you type the whole thing from start to finish. Aren't you glad you live when you do? Yeah. Now they're in antique stores, or they're used as decorations, right? But anyhow, script L and script N is the norm for that. Why LN? People don't really know. One guy that started out using logs only used the L. And so some think that somebody else along the way said, hey, let's put the N with it for natural log, even though the L is first. Because they use the L for logarithm. So they just use the L alone to show a natural log. And then again, they say somebody else tried the N. Others say it's Latin or French, whereas instead of natural log, it's like log natural. But they really not, I'm sure there. So whatever the case, it's ln. All right, ln. And again, the base is E. So we don't show the base, but if you did, I should make that in green. We don't show the base, but if you did, it would be there. It would be an E. But again, you're not going to see that. They expect you to know when you see the ln that the base is E. The more valuable thing is to understand what it is. So what do I have here? I have e to what power equals 7. E to what power equals 7. That's really, again, converting, right, from exponent, from log form to exponent form. And as I told you guys way back in the beginning, and that's the key to everything this chapter, is to be able to convert between the forms. So if you're still struggling on that, if you got your quiz back and you missed questions 6, 7, 8, 9, you're really killing yourself. And you can memorize that. It's not hard to memorize, but you got to know that. If you're missing questions 6, 7, 8, 9 on the quiz, you are torpedoing yourself, and you're just interrupting all your understanding. Because what do I keep doing? I keep going to exponent form to help you to understand, and that's what you need to do. It's awesome. We're getting there. Hold on there. Okay, Babalu, he says. All right, so each of these are going to have an E base, right? We're looking really for the exponent. Oh, in this case, it would be x because we gave a value. In 3, we're not sure whatever variable you want. And the result in the second one is 5, and the result in the third one is 1/3, right? Again, I'm just changing form from log form to exponent form. The point is, what's the base? The base is E. What's the base? The base is E. What's the base? The base is E. All right, where does E come from? So E is often called, I know it looks like Euler's, but it's Euler's number, after Leonard Euler, who was a guy that used E, kind of came up with it, kind of. There's a little bit of dispute there as well. But that's where the E came from the guy Euler. And what is it? It's an irrational number. Can anybody explain what an irrational number is? I'll help you out. It's a number that can't be represented as a You're so bad with your number sets. Okay, so our number sets are real numbers, right? And then real numbers get separated into two sides, the irrationals on one side and the rationals on the other. Under the rationals come the integers, then under the integers come the whole numbers, then under the whole numbers comes the natural numbers. Right, so let me go bottom up. Natural numbers, 1, 2, 3, 4, 5 and up. Whole numbers, add 0, 0, 1, 2, 3, 4, 5 and up. Integers, add the negative numbers, -1, -2, -3, dot, 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 0, 1, 2, 3, dot, dot, dot. And then get to the rationals, and rationals are fractions. Anything where you have an integer numerator divided by an integer denominator. Anything that can be a fraction is a rational number. Therefore, an irrational is anything that cannot be a fraction. Square root of 5 is an irrational number. You know, again, if you can find a whole number divided by a whole number to exactly equal the square root of 5, you will be famous. You might even win the Nobel Prize. Be rich. But nobody's found it yet, so I don't know if you want to waste your time. But irrational number, right, you can't represent it as a fraction, and that's what Euler's number is. There's no integer numerator divided by an integer denominator that will exactly equal the value. So it's an irrational number, but it is real. Versus imaginary numbers are not even part of the real numbers, right? We did imaginary numbers. What are they? Square roots of negative radicands, right? Or even roots of negative radicands. All right, anyhow, it's an irrational number. It's also a transcendental, not the meditation, all right? It's also a transcendental number like pi, because pi r squared, right? Or pi squared, only if you're doing area. All right, geometry. Nobody else caught that though, so I'm wondering. Okay, what is the value of E? We're gonna stick it up there in a minute. The 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 closest concept of E is what's listed right here. So does anybody remember what this red E symbol looking thing means? It is Greek. It's the Greek letter sigma. Does anybody remember what it stands for? You had it back in Algebra 1 or pre-algebra, one of those two. It's in both courses right now, but I can't remember if you guys had the new Algebra 1 course or not. Anybody know sigma? By the way, you'll see those. We're going to deal with those next chapter, by the way. Sigma is summation. It means add all the terms. It's summation notation. So sigma means we're adding a bunch of things up. Okay, you guys remember what the exclamation mark is, right? The exclamation mark is what? Factorial. And what would, like, explain in words what 5 factorial would be. Can anybody do that? Times 3 times 2 times 1. Remember that? 7 factorial, 7 times 6 times 5 times 4. Okay, so this is a series. A series is a thing that continues on. So here's what you do. You take, I'll do this in black. You take your, what's in the parentheses? N is the variable. The bottom of sigma tells you what value to start n at. So what value do we start n at? 0. So it's 1 over 0 factorial. Take your red plus. Now we got to do the second one. So we went from 0, now n is 1, so now it's 1 over 1 factorial. Take your red plus, and now it's 1 over 2 factorial. Take your red plus, now it's 1 over 3 factorial. Let's see how far I want to go. Take your red plus, and then it's 1 over 4 factorial. Hopefully you're not squeezing these in real tight, because you can see I'm not. And we'll go one more, plus 1 over 5 factorial. And we'll go plus dot, dot, dot. Right, it goes on forever. It's an infinite series. And sigma says add them all up. Okay, go ahead and punch 0 in your calculator, hit the factorial button. Did you get 1? 0 factorial is 1, correct? So everybody knows 1 divided by 1 is 1. All right. So that first number is a 1. Punch in 1 factorial. See what your calculator says. 1 factorial is 1. It's also 1. So everybody found the factorial button on their calculator? You all have one. End of the exclamation mark, or just the exclamation mark, or X to the exclamation mark. Some of you have to go into the menu for your statistics menu. Right? What's the menu button that you're hitting to get to the statistics menu? Anybody? Can anybody say what you're hitting on your calculator? It's like a PBR button. Is that what it is? Right. Everybody find their factorial button? 1 factorial is 1. So 1 divided by 1 is another 1. Okay, 2 factorial. 2 factorial is 2. So what is 1/2? 0.5, right? All right, so let me pause for a second. Here I'm showing you the value of E, right? And I only have given you the first decimal point, 2.7. Well, do you see the 2 already? 1 and 1 is 2. And now we have 2.5. We got to end up at 2.7 and change. Okay, 3 factorial. 3 times 2 is 6. So what is 1/6? And 1/6 is 0.16 bar. 0.1666666. So you see our value right now is up to 2.66, right? 2 plus 0.5 plus 0.16 is 2.66 total value. Now do the next one. 4 times 3 is 12, times 2 is 24. What decimal is 1/24th? And it's 0.0416 with a bar. So now we're up to 2.716. And we'll do one more. 5 times 4 is 20, times 3 is 60, times 2 is 120. 1 over 120 is 0.00138 bar. 0.00138 bar. And again, we're not going to keep going. But as you keep going, if you take it to infinity, it equals E. Am I ever going to ask you this again? No. Will I ask you the value of E? Absolutely. And everybody has it right at their fingertips. Value of E is 2.718281828. And I need somebody who's got a 10-digit calculator. Yours goes past 8. Anybody have a calculator? Your screen, you can see all the digits. Okay, Andrew, hit your E to the X button, right? It's the top of your LN button, and then punch in 1, right? Make the exponent 1. So E to the first power, and read your screen for me. Can you scroll past it? Won't give you anything past it. All right, can anybody's calculator go past that last digit? Again, you're doing a E to the X, and you're making the X 1, so E to the first power. By the way, this is how you'll all answer the question when I ask you on a quiz or a test, what's the value of E? You'll punch in E to the X button and punch in a 1. Anybody's screen go past those digits? Okay. I think the next digit is a 5, and then I'm going to put ... This is a non-repeating number, though it looks right there like it's a repeater, right? Because it does the 1828 2 times in a row, but that's it. This thing doesn't repeat, just like pi doesn't repeat. Okay, so I think the next number is a 5. Your book may say it. But that's the exact value. So what is E? 2.71828, roughly. And believe it or not, it has a lot of value in some formulas. And we'll get to those formulas next week when we deal with some practical applications. That's the last lesson of everything. All right, that's enough of that portion for tomorrow. That gets us going as far as we want. Worksheet tonight.